Welcome to the Cosmic Pi Podcast, episode number 29, season number 2. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
So just as a disclaimer, Robert, you want to start that before we introduce our special guest today?
I suppose we can do that. Let's see, the opinions expressed in today's show are those of myself, Wayne, and Markus, and not those of the University of North Dakota or the state of North Dakota or any other entity, just us, so blame us.
That means we have carte blanche to say anything we want.
No, it means just the opposite.
Oh, darn.
It means just the opposite, I think.
So today we do have a live chat feature that's running, so if you have any questions or comments I'd like to ask throughout the podcast, feel free to use that. But today we're going to introduce here our special guest, Dr. Markus Allgaier, Department of Physics and Astrophysics here at the University of North Dakota. So Markus, thank you for doing this.
Of course.
So you do want to introduce yourself, kind of give people an idea of what your specialty is?
I can absolutely do that. So I am what we in the field call a laser jock. So the short summary here is that I point lasers at crystals. And through the years, the types of lasers have changed and the crystals have changed, but the concept was the same. The way that started, my background or my training during my undergrad started in material science. So I first learned a lot about semiconductor materials and how they're used in lasers and microchips. And at that time, I pretty much thought that lasers were boring because all I was taught about were the materials that one part of the lasers was made out of. And that is kind of boring. Later on, kind of out of necessity, I switched fields into more interesting things, and I wanted to learn about quantum science. I ended up doing a PhD program in applied physics, where I did research in quantum optics. So that is optics for the purpose mostly of telecommunication with very small amounts of light. And that's the field where I got stuck ever since. And I learned how to push laser pulses and photons around. And now I'm developing light sources for communication with photons using the quantum properties of light.
Now, Markus, I noticed in the news last couple of days there was this research that was published showing you for the first time they're indicating, they're making the statement that we actually see what a photon looks like. Did you notice that in the news?
I saw that. Yeah, that comes up every couple of years. I almost thought I've seen the pictures or the videos before.
Oh, that's interesting. So what does it look like? Can you describe it?
What is a photon? That is a very good question. Or what do pulses of light look like? Years ago, I heard a talk from a professor in England who runs a big quantum optics lab, and he said that a photon is something that makes a photon detector go click. And a photon detector is something that goes click when it gets hit by a photon.
Talk about a circular.
Yeah. Oh, we have a machine that goes bing.
That's funny.
Yeah. I've watched too much Monty Python, so
remember that joke that we said once about photons? Yeah, photons have a mass. I didn't even know they were Catholic.
Right. And yeah. So okay.
So photon. Yeah, so I was just going to say, so there are lots of stuff that's been in the news, not just the last few days, but essentially last several years, is the ability of people to communicate and try to hide that communication. So you could think of military applications, for example, or maybe some intelligence service, and you want to communicate with a satellite that's in orbit around the Earth, but you don't want that information to be intercepted to the point where people can know what that information is. It's just all scrambled, or at least they can't make sense of it. Isn't that a big thing now in quantum optics related to that enterprise?
That is one of the big applications. And one thing that's very important for me to point out, it's not just military applications or intelligence, right? We want all of our communication to always be private. Like you as a regular person and me, we have a right for our communication and our data to be private. In some countries, that's respected more than in others.
Yeah.
The USA lies somewhere in the middle. of the field there.
Right.
Yeah.
And that's not just a personal preference, but you don't want your credit card number to be all over the place when you buy Christmas presents on the internet, right?
Or,
Right.
And nowadays, not most of our communication, but I would say the backbone of the internet happens optically. We use optical fibers for communication. So that's already where optical communication comes in. And almost all of the communication that happens these days is encrypted, meaning it is to some extent private.
But I guess
Right.
the idea is you don't want to like have people advance algorithms. If you think of that, like AI, right, is the famous buzzword nowadays. Everything's AI, AI, AI. I'm waiting for AI generated cereal. You know, I'm sure it tastes better than non-AI cereal.
right.
That somehow with AI or machine learning or deep learning, all this other stuff, and this is not even getting into the realm yet of quantum computers, that they can hack a lot of these encrypted systems that people use today.
Mm-hmm.
So do you see?
It's a possibility,
Yeah.
and there are many places where one could think of attacking. So the protocols themselves that are used for encryption, they're considered secure, but a lot of them lack the mathematical proof that they are secure. So often the reason why we think they're secure are not fundamental, but there is a hardness argument that they're not actually unconditionally secure, but that it's just very hard to attack them. And then the much simpler version is usually the devices that we use are vulnerable, right?
Right.
You can only draw a certain size bubble in which you know everything is secure, but at some point you have to read your information on the screen of your phone, and someone might be looking over your shoulder. So that's an entirely different story. So where quantum optics could come in to make things more secure is really comes down to the very hypothetical question if the protocols that we use are fundamentally unconditionally secure or not. And that is a hard question that mathematicians have been banging their heads against for decades now. For example, RSA, one of the companies that is behind a lot of the encryption that forms the backbone of how authentication works on the internet and how you know that the website that you're talking to is actually the website that you think you're talking to. They have always put out these challenges where if someone can crack their algorithm, they give you money. So they can advertise their security by saying like, we would pay someone $10 million if they can do it, but no one can do it so far, and only their very oldest, very simplest algorithms have been cracked in that way.
Right.
So where the nuance comes in is that we have to come up with something better. If someone comes up with a better way of attacking the encryption that we use now, and on top of that, it would be nice to have encryption that is unconditionally secure, meaning that the security doesn't just rely on an argument of hardness, but on impossibility, that it's like certifiably certain that this protocol is at its core unhackable.
So that would be even with a quantum computer, then theoretically, right? That would be unhackable even at that sort of limit.
Mm-hmm. Yep, even with that.
Yeah.
Yeah, I once sat in on a lecture where they were talking about the mathematics of codes and code breaking, and I got to admit I got very little out of it except that there is a mathematical science behind it, and that was kind of mind blowing. I won't lie about it, but that's another story.
So how does the quantum communication with satellites actually work? Can you demonstrate or maybe expand on that a little bit?
Mm-hmm. So there's probably thousands of different protocols that different people and groups have written down on how you could do that. The easiest to explain is the oldest, which is called BB84, and it escapes me right now what the B and the B are or who the B and the B are. But the protocol is from 1984, and it does not actually involve any quantum states of light or any quantum features like entanglement. It's just the idea is you, instead of what we do now, which is sending very bright pulses of light for communication. Each pulse encodes a bit. You would send a very tiny fraction of light, which is called a photon. So the smallest excitation that you can have in this electrical field that makes up the light that you send. And the very simple idea is that you encode the information on some feature of that photon, for example, polarization, or it could be when you send that, or the color of the light, could be any property that light has. And because there's only that one photon, you can't split up the information. So one of the very fundamental feature of this photon being the smallest quantity of light that you can produce is that you cannot split it. So what an eavesdropper can never do is obtain mutual information with the receiver. It can go either direction. So if the receiver, the intended receiver of a message, receives the bit that is encoded of that photon, they know that no one has been listening in. And so that is based on something called the no cloning theorem. So I cannot copy the quantum state of light.
Okay.
I can try to read it out, but all the ways we have of reading out the state of light that's a photon destroy the photon. So the security comes from the intended receiver knowing if they lost any information on the way or if someone has been listening in.
That is actually kind of cool.
Yeah.
But of course, that narrows your bandwidth, the rate and the level of information you can send too, doesn't it?
It is a very narrow application because when you think about it, that only tells you if you've been spied on, but it doesn't
Right.
It doesn't keep anyone from intercepting the message. So the application for this is what we call quantum key distribution. So that is another nuance that I can try to explain. The encryption algorithms we have are actually really good, no matter what kind of tools you envision could be around in the future to hack those. In the worst case, what would be reduced is what we call the cover time. So the cover time is how long you want your information to be secret, right? If I send you a text message, you don't need that information to stay encrypted for the next 20 years. Like you're going to read it and then it can be deleted and then everything's fine. For government secrets, that might be an entirely different story. If you now could encrypt information that was encrypted or decrypt information that was encrypted in the 1980s, that might still be a problem. But so if you have any way of attacking the encryption algorithms we use, it would merely shorten the viable cover time. Because even a way that is way better than what we can do now for attacking these algorithms by brute force would still take a little bit of time. So instead of, in theory, taking 10 million years to decrypt something, it would now take, I don't know, a day. But even the encryption algorithms we use now, they recycle their key material very fast and produce new ones in case the key material is not secure anymore. So what quantum key distribution does, it fills that small gap when you lose the security of your key material. So imagine encryption to work in the way that I take a letter I want to say that I want to send to Robert, and I put it in a box and I lock the box with a key. And Robert has the same key. So I mail Robert the box and he can use his key to open the box and take out the message. That's in theory how it works. Now, if we're not sure if someone has made a copy of one of our keys, then we have to use a different set of locks. We have to get new locks for our boxes and new keys. And that is a process that is actually very hard if you're in two physically different locations.
Yeah.
If Robert and I can get in the same room, we could just make new keys and now we know no one else has them, as long as we trust each other not to give someone else copies of the keys. If we're on opposite sides of the country, that's kind of hard to do.
Right.
Because you need previous encryption to send the new keys in a secure way. So all encryption in a way relies on old encryption.
Which could have been broken, and yeah.
That is literally what happens. New key material is in some way created from random material and from old keys. Because, for example, you need an old session when you're talking to a website to certify the new session.
Right.
So most key material for encryption is generated from old key material.
That's kind of
And
crazy.
they're very complicated and sophisticated algorithms to do that. But it is, in a way, a fundamental problem that if you have nothing old that's still working to base new keys on, you're in a pickle. So that's the one little gap that quantum key distribution can fill, is that you can send someone a key and they can tell if someone has been spying in on that communication.
Okay.
So that the receiving party has a certification that the key they received is secure and private between the two parties.
But let's say a party sends information that's top secret to a receiver. The receiver determines that that information has been viewed, but that information is still lost. Like somebody got that information that you didn't want to have, right? There's no way of preventing that. Is that true?
There is no way in principle to prevent that.
Yeah.
Yeah.
And I'll give you, even now, I'll give you a very simple example. The reason why you can't attack any encryption algorithm by brute force, which what we call an exhaustive key search, so that's trying all the combinations, is that there's so many combinations that it would take you billions of years to try them all out, even if you can try a million a second. But there's nothing in principle that prevents you from guessing it right the first try.
Right. That's something that a lot of people miss about statistics is, okay, it would probably take you a billion years to go through all the codes, but there's nothing that says you don't get it on the third try.
1 in 10 to the 30 is not 0.
Right.
Yeah. And the other thing is, it's not like there's a way of knowing that somebody's tampering and then you destroy that information so that even if they manage to unlock it or find the right key, that somehow that information now is gone, right? Or it's been scrambled or randomized or whatever.
Right.
There's no way of doing that because you wouldn't know the difference between Robert receiving and unlocking it and therefore allowed to look at the information versus I'm in the middle somewhere and I grab it and I went and snuck and took a backup of Robert's keys, except I didn't know which key it was and he had 10 of them and I try all 10 of them. Eventually I'm going to hit the right one and then I view that information.
Right.
Exactly. So the only handle you really have is you need to be sure who you're talking to. You need to be sure there's no one in the middle who just poses as this other person. And if you have a secure line of communication, you need to make sure that the key material for that gets constantly renewed and updated.
Right.
Yeah.
There's a lot to it.
There is.
Who knew?
So
there is a lot to it, yes.
Yeah.
So I know NASA recently has been publicizing that they did the first time like transmission over a laser to communicate with various spacecraft. So that seems to increase the bandwidth a lot more than what you can get with just sending like radio transmission through the Deep Space Network or something. So
yeah, so that's an entirely different story from the quantum communication, right? The quantum communication does not give you a faster internet connection to a satellite, sadly. It just gives you a more secure one.
Right.
That's very, very slow.
Okay, yeah.
And for example, there is a satellite in orbit that can do certain quantum key distribution protocol that was launched in China a couple years ago, and what we call the secure bit rate. So how many secure quantum bits can it actually receive per second is something like less than 1. So it takes a couple hours and a couple overpasses to transmit an entire key.
Oh, wow.
Yeah.
That.
So we're not there yet, but classical
that's...
communication with light is entirely different story. I don't rely on these like very small packets of light. I can just crank up the power until I see something. So what NASA is gunning for there is a 1 terabit per second connection to a satellite.
Okay.
Yeah, and there you have to be in direct line of sight. Is that true, or can you have like orbiting platforms that kind of reflect that laser light somehow and then get picked up by the receiver?
You could think about that, but in some way you still need a line of sight. But that's not a huge issue because you also in some way need that with most radio communication.
Yes,
right? I can't talk to someone who's on the other side of the world, at least not with with a very high bandwidth connection. I'm not talking about like shortwave amateur radio.
Right.
Yeah.
I was about to say the AM will do
high-speed
that,
data.
but
Yeah, so you could do
Yeah,
like
we're not doing.
we're not bouncing
Meteor
off the
burst shortwave.
ionosphere.
yeah. So it's, let's say a Mars orbiter, and they took lots of images of the surface high definition. So there's lots of data. Once they're in line of sight of the Earth, they could do essentially a core dump.
Exactly. That's the idea.
Okay.
Okay.
Yeah, that makes sense.
That makes a lot of sense.
Yeah, for sure.
So if you have a spacecraft or a satellite that's in a low Earth orbit, then the line of sight you get while it passes over is a couple minutes, depending on what the orbit exactly is and how it passes over you. And a couple minutes is not a lot when the radio wave connection you have now is about the equivalent of a early 2000s internet connection.
Thanks.
Oh my.
But when you have a terabit per second, which is 1,000 times faster than Google Fiber, that gets you somewhere.
Right.
Is there a limit to that? Like, what's the most that you could do in the ideal situation for data transfer?
Oh, that's a good question. I think at some point you run into how fast you can turn a switch on and off.
Right. Yeah. That makes sense.
Yeah, so you run into speed of light limits, essentially, right, for that circuitry.
Well,
Not that, because let's say let's assume in the simplest case that, and that is something that is happening, that the light is encoded with on-off keying, meaning the light being off is your 0 and the light being on is your 1. I could turn my light on and off before the light actually arrives on the ground.
Right.
Which you absolutely will. And that happens for fiber communication. So if your standard fiber bandwidth is 1 gigabit a second, that means that you have 10 to the 9 symbols a second being sent. That means the duration of one symbol is a nanosecond.
Right.
right.
Which means that with the speed of light, that means that if you draw that, how far does the light get over the duration of one symbol? It gets about that far. It's about 30 centimeters or a foot.
Yeah.
Right.
So if I send an internet connection through a transatlantic optical fiber cable, there are many symbols on route at any given time.
Okay. That makes sense.
Yeah, you can think of that as the width of the pipe, right? So you get the flow of information, the bigger the width and the more, that's more the bandwidth, right? As we would say, I guess.
But bandwidth is wavelength dependent, isn't it? Isn't the bandwidth wavelength dependent? So you could get a higher bandwidth by going to shorter wavelengths? But there's a problem with that too.
You could. There are a lot of problems with that.
Yeah.
For our optical communications, we kind of settled into a very convenient window in the near infrared where glass is very transparent and where we can make cheap, very powerful lasers. So there are different reasons why we settled on that. And it turns out that it's a very good window for optical fibers when you're going through glass, because the type of glass we use is very transparent. Like, you lose almost no light if you go a couple miles through a fiber.
Okay.
When you go through the atmosphere, you're actually at the edge of a water absorption band. So you're losing about half the light when you go through the atmosphere.
Okay. Yeah.
But it's still the better choice because we have all the technology there. And that's one of the things, what I mentioned, the fast switches to turn the light on and off and encode the bits. That would probably be the bottleneck.
Okay. Yeah, I got to admit, I was thinking, why not use a UV laser, and forgot all about the fact that the ozone works both directions. And so you couldn't do satellite communication with UV because the atmosphere is awful opaque to UV.
Sure. If you just wanted to go for the lowest loss in the atmosphere, you would end up
in the radio.
Somewhere in the I'm not sure how it compares to radio, but somewhere in the middle of the visible spectrum.
Yeah.
Kind of blue green.
Okay.
Yeah.
It just, like I said, my mind blanked a little bit there. It was like, well, why not just use the higher bandwidth at the lower frequency setting? And then was like, wait a minute, you can't transmit that through the atmosphere either.
Yeah, so you worry about like water vapor and carbon dioxide. So
Right.
if you think of climate change, more carbon dioxide being put up in the atmosphere, that's going to have a more negative effect on this type of stuff.
Yep.
But in fact, can't you use that, Marcus, as a probe? Well, this kind of gets into your work, right? That you use LiDAR or whatever and things like that, right? Can't you use that as a probe to measure what is the condition of the atmosphere at any given spatial location, at any given temporal sort of marker, by transmitting information through the atmosphere and seeing what you get at the at the other end type of thing?
You can absolutely do that. And I like that you brought up CO2, because CO2 is actually a hard example because the absorption lines of CO2 are fairly narrow.
Okay.
So the challenge with doing these kind of measurements is that you actually have to hit that line. So if your laser is detuned even a tiny bit, then you won't see anything.
Okay.
Okay.
That makes sense.
Yeah.
Yeah.
Yes.
I mean, that gets into spectroscopy. If you got narrow lines, they're hard to resolve.
Yeah, you have to be ready. So your bandwidth or whatever, your delta lambda is going to be relatively small. And so that makes it probably more expensive, right? To build something that you can tune to a very specific narrow range of wavelengths.
Mm-hmm. Yeah.
Yeah.
I mean, making narrowband lasers is always a little bit harder than making a broadband one. So when it comes to telecommunications, the lasers don't have to be good. They just have to be reasonably stable and affordable. Those are the boxes that you want to tick there. You don't need a really high quality, long coherence length scientific laser to talk to someone. That's not something that you need. In fact, what I mentioned for the laser communication, the on-off keying, you don't need any coherence length whatsoever. It's not a coherent measurement. So you don't need coherent light. You could do this with an incoherent light source like a light bulb.
Oh, interesting.
Which we've been doing for centuries,
It just turns out that we can do
yeah.
incoherent measurements, so just measuring the amount of light, not the intricate workings of the wave nature of it. We can do those a lot faster than the coherent measurements.
Right.
Yeah. Now, could you take like a normal laser, quote unquote, and then make it so that the light that leaves that instrument is a very narrow wavelength or frequency range by putting extra machinery, for lack of a better word, so that the laser itself is a cheaper laser, but it goes through a filtering process, if you like, to only allow that very narrow range of wavelengths.
Mm-hmm. You can do that, and that's actually something that we're getting started to do here. So you can always build a cavity. So you have a set of two mirrors that in a way trap the light. So it bounces back and forth. And you get an interference effect between the back and forth bounces in the cavity. So when you imagine the light as a standing wave in between those, the light has to be a certain wavelength for that standing wave to fit into that cavity. So that's the way how we usually make very narrow band lasers. And we're now getting started to making our own mirror coatings for these cavities here in the new clean room. But so the fun thing is that gets you down to a certain line width. So let's say you wanted to do some spectroscopic measurement where you need to sit on an absorption line of a molecule like CO2. Those wouldn't be particularly narrow. So you can probably get away with having a cavity that's tuned to that resonance. Or you could even have a little cell of that gas so you can monitor how much light gets through when you get a signal that you can steer your laser on to stay on target. But there are some applications, for example, with my previous workplace in Boulder at the National Institute of Standards and Technology, there are folks who built lasers to compare different atomic clocks.
Oh,
So now your laser has to be, in a way, a measuring stick in time that's at least as precise as the atomic clock. So in the way you're building just a better clock to compare your two clocks to. So what you do is you compare a laser to clock A and also to clock B, and the laser is actually as stable as the atomic clocks. So now you can compare them even though the clocks are in different locations and very bulky. So now you still do it the same way. You use these cavities and these mirrors that form standing waves that force the light to be at a certain wavelength. But if you want to get more and more precise, you run into the issue that everything moves. There's thermal movements of the mirrors. There's mechanical movements of the mounts that hold those mirrors in place. So now you have to work on all these details. So what they resort to is they mill the mount for these two mirrors out of a solid single crystal of silicon. And then they put this assembly that's about the size of a baseball into a cryostat and cool it down to almost absolute zero to freeze out any mechanical motion in there.
Almost reminds me of the gravitational wave detectors.
Yeah, I was about to
It is
mention
exactly
LIGO.
like the gravitational wave detector, just smaller.
Yeah. It's, with LIGO, they're down to the point where they're measuring the quantum fluctuations in the surface of their mirrors. And it's like, holy cow.
Exactly. If you want your line width to get more, the kind of two applications to the same problem. If you want to make a very stable laser, you're trying to make a cavity that keeps the light constrained. If you do LIGO, you have a cavity that is also very stable, but now you're looking for the intensity of the light to change, or some properties of the light, because the length of the cavity changes with the gravitational waves that pass through it.
Yeah, you want to eliminate all possible effects that change
that cavity size.
Except for the gravitational waves.
Yep.
So in a way, LIGO can go the easy way and make the cavity bigger to make it more sensitive, which may not be a very practical solution if you try to not break through the walls in your lab.
Yeah, I'm just thinking of they have the light bouncing back and forth between these two mirrors on these long arms that are like 4 kilometers in length.
Right.
And what you really want, of course, is try to get that whole thing into space if you could do it. And you can increase the arm lengths by, millions of kilometers, right?
Yeah.
And have independent satellites that are shining lasers from one to the other to the other. Think of a triangle is what I'm thinking of in this case. Looking for subtle changes in the distances between
I see
those
what you're wanting.
mirrors.
You're wanting closure phase on gravitational waves so you can make pictures with it.
Yeah. I wanted to get away from the Earth because the Earth is really a big noise source, right?
Yeah.
You think of tremors and even people going down the interstate in 18-wheelers and stuff shake the ground, and that causes problems, right?
Yep.
False
But
detections.
that's why we built 2 LIGOs, right?
Yeah.
Right.
Because the idea is that that big semi-truck is not going to be in front of both of them at the same time.
Yeah.
That's it.
But I mean, obviously there's a floor, a noise floor, and you're trying to get more sensitive than that. And the other thing is you want more than one. Is that way you can tell the rough direction that these gravitational waves came from, and then point other telescopes looking for, that's how we saw the merging of the 2 neutron stars in optical telescopes and
Right.
other wavelengths, because we had a rough idea from the 2 detectors where the signature was coming from. So in the future, right, with multiple gravitational wave detectors, whether in space or not, we should be able to isolate even better where we're picking up the signal from, and then look in the other band to see if there's anything, that you can see EM-wise, right?
Right. So, yeah.
So
We might get that somewhere, and in quantum optics, in a way, LIGO is one of the things that we're the most proud of, because LIGO uses some quantum properties of light to become more sensitive. So we can always say at least we did one thing that someone found useful.
Yeah, got the Nobel Prize, and you open up a whole new era in astronomy.
Yeah,
But
and who knows? Maybe sometime in the near future, maybe we'll get the LISA mission, which is that exact proposal to build a bigger LIGO in space.
Right.
Except it's getting a little bit crowded around the Lagrange points. They're very popular lately for new missions.
Yeah,
for a reason, but yeah.
I wonder if you could somehow send them on an independent orbit around the sun, like have 3 of them together. It's a cluster, if you want to think of that, or somehow. I mean, it just makes it more complicated, right? If they're spread out on their own orbit, but I'm sure you can map it eventually, fairly precisely.
Yep.
And
In a way, you don't really need the legs of the triangle to be stable to make a detector like LIGO. You only need to know very precisely where the 3 points are.
Right.
Yes, right.
At any point in time.
Right. So if there's a time rate of change of that separation, as long as you map that to some precision, then anything on top of that would be the gravitational wave.
And it is a common challenge that we're facing with laser satellite communication, and especially quantum communication, because there's so many good and promising protocols that require some kind of interference measurements. Let's say I shoot a photon to a satellite and someone else shoots a photon to the satellite, and they have to arrive there at exactly the same time. And that is hard because they're usually very short pulses. And the reason why that is a challenge is that the typical position knowledge that you have for a satellite is about a centimeter.
And
that is a precision that you can pretty easily get
Yeah.
to just with GPS and star trackers,
Right.
and fairly available means. You can have position knowledge that is a centimeter on a very small and affordable satellite by now.
Right.
So if you want to get down to where you're doing interference on the order of the wavelength of light, the wavelength
Yeah.
of light is
That's-
a micrometer.
Right.
So-
That's what I was thinking. Centimeter
Exactly.
is still a couple of orders of magnitude too large, you know?
Yep. 10 to the minus 6 meters, not 10 to the minus 2.
Right.
So
yeah.
missing 4 orders of magnitude of position knowledge, and even the 1 centimeter position knowledge is only something you have when you're close to the Earth.
Yeah.
Yeah.
Because
So
if you put something at the Lagrange point, there is no GPS signal.
right. So it'd be hard to imagine how you even arrive at that needed precision in the future.
Yeah. Except I think it's coming. I mean, we've got interferometers that are working on, you know, micrometer and nanometer scale.
What about the arrival of pulsar signatures independently for each satellite? If you think of a triangle, and you look at like 60 pulsars or something at the
If
same
you could make it
time.
work.
You know, I'm just wondering, because that would give you your 3 spatial dimensions,
Yeah.
right? If you looked at pulsars distributed in the right way. So I wonder what that would buy you in terms of knowing your position relative to the 2 other satellites in the same time.
Sounds like a grant proposal.
Yeah.
I think this is a very good question to bring up, because when you think about the 3 satellites independently, you run into issues with the speed of light, right?
Yeah.
What we usually do in optics, if we try to interfere waves and our lasers and our optics and our laser table are not perfectly stable, we just measure for a shorter duration.
Right.
Right.
Because everything's stable and fixed in place if you don't look for long enough.
Yeah, I've had that discussion with students in the labs. You know, it's like, if we look at a small enough piece of a circle, what does it look like? And
It is straight.
it looks like a straight line.
If I take a pen and I drop the pen, it stops. But if I took 2 photos that are a millisecond apart, it would seem to be in the same place.
Right.
Yeah.
So what's the time that you really need everything to be stable for to do these optical measurements on the order of the wavelength of light? So if I'm doing things on my laser table, I need things to be stable and well behaved and coherent for as long as it takes the light to get to the end of the table and back, which is a few nanoseconds. So that's not very long.
Right.
So you don't need a very coherent or narrow line width laser or very stable optics.
For
But
very
now if I
long.
want to do a measurement for a LIGO in space where the arms of my experiment are millions of kilometers long, things still travel at the speed of light. So I need things to be still nice and coherent and well behaved from the time it takes that signal to travel from that satellite to that satellite. And if that's millions of kilometers, then that's a very different scenario.
Yeah, it's minutes of time.
Minutes of time. Right.
You know, many seconds anyway.
We'll get there. I'm confident. I'm looking forward
And if
to
you
it.
ask an optics person what a long time is, I would tell you a microsecond, maybe. A microsecond's a long time.
Well, Einstein said it's all relative.
Yeah.
Yeah.
Now I know
Light would go from here to New York City in a microsecond. It's so far away. It's so long.
Yeah.
Yeah.
Now I know, Marcus, you do a lot of work related to glaciers. In fact, I know you go on field trips like to Greenland and things of this. Do you want to explain a little bit about that side of your research?
Yeah. I'm already glad that we got to talk about so many different topics, because you're hopefully starting to see the picture that it's all the same language and all the same concepts, talking about timescales and lasers and pulses and different trait spaces of how stable and how fast and how slow and how far away things can be. And so a lot of a lot of this stuff that we learned in the optics lab trying to do quantum communication, you can apply to other fields like measuring gravitational waves and measuring greenhouse gases in the atmosphere. And so another application that we found is to measure the optical properties of scattering systems. Scattering systems are things that are made out of particles that scatter light. And the two big examples are snow and clouds, which are made out of particles made out of water, some liquid, some frozen. And the properties of these systems are really important for climate models, for weather forecasts, because that is in a big part what governs the radiation balance of the Earth. So an example is how much light a cloud reflects and transmits is defined by the size of the water droplets and ice crystals that make up that clouds and the density of those particles in the cloud. So if you have more particles that are closer together or smaller and larger particles, that changes how much solar radiation is transmitted down to the Earth or absorbed in that cloud or reflected back. So how our entire Earth system responds to the energy input from the sun depends a lot on these scattering systems. And other scattering systems are snow and ice, which covers a pretty large portion of our planet, depending on the season, or the ocean, because it has particles in it that reflect light. It behaves in a very similar way. So one of the bottlenecks to make better predictions of the uptake of solar radiation in those systems is to know the properties of those systems. And so what we get to do is to support a NASA mission called ICESat-2. That's the Ice, Cloud, and Land Elevation Satellite 2. Number 1 is broken. To get a better idea of these systems, snow and ice in particular, what their optical properties is, and how that satellite can make measurements of those systems.
Okay.
So in other words, so the satellite is going to look at light scattered off, let's say, Greenland, and it'll be from areas which are, of course, hard to get to, so very remote areas, and you can measure characteristics of the snow coverage then from the type of scattering that occurs, or the age of it, this kind of stuff. I mean, how does that work?
It's a little bit more complicated. So to measure things like snow cover, all you need is imagery. So they're older satellites that just measure passive things that can give you a handle on that. So what ICESat-2 does, it carries a laser altimeter. So it has an active sensor, so it can emit pulses of light. So the purpose of ICESat-2 is to measure very precisely the elevation of the Earth's surface, down to less than a centimeter accuracy. And the way it does that, it emits green laser pulses that then, after they pass through the atmosphere, hit the ground, and that light gets scattered back into space. Of course, it goes everywhere, so most of the light will leave the Earth again. It will just not find its way back to the satellite, but it has very sensitive detectors, similar to the ones that we use for quantum communication, that can detect and time the arrival of that reflected and backscattered signal. And the satellite knows where it is and where it's pointing. So with all this information, together with the round trip time for the light, it can calculate very precisely what the elevation of that point that it was hitting was. And so now you have a very accurate measuring stick for how the surface elevations of the Earth change, for things like sea level rise, ice sheets melting, frost heave are other examples, deformation from volcanic activity. There's all kinds of applications. You can even measure the depth of the ocean down to 100 meters.
Wow. So I can see like changes, we hear about Antarctica where different parts of the ice shelf, splits off and so on as a signature of global warming. That this satellite would be able to measure carefully any deformations that could say, okay, there's something happening here, and can alert scientists to maybe spend some extra attention on that part of the ice ice sheet.
And it can do it accurately and continuously and everywhere at the same time. So that's the big deal, right? If I want to know if the surface elevation changes outside my front door in North Dakota, I could use a GPS receiver and do that at different times of the year or multiple years, and that would tell me something. But it's very hard to put GPS receivers everywhere in Greenland or Antarctica. So that's where those satellite missions shine, that they fill in all the blanks where we don't have any opportunities to go in the field all the time.
Yeah.
And they give you that information continuously and then basically in real time. So one of the big things that came out of the mission is that there is a data product that tells you the level of every lake and artificial reservoir in the world at the same time.
Oh, wow. That's neat information.
Yeah, so you can monitor drought conditions.
Yeah.
Right? Keep an eye on stuff.
And I'm thinking, I found out that the Earth's surface over continental U.S. and Canada and everything is rebounding because of the weight of the ice sheet from the ice age. And it's actually coming up, so you can get information about that sort of thing too. How fast the rebound is going.
Rebounding since that ice disappeared only recently on geological timescales, like a couple 10,000 years ago.
Yeah. So this satellite obviously is in polar orbit. Right? So
it is almost in a polar orbit, yes.
Or almost in a polar orbit. So it's at a very high inclination from the equator.
Mm-hmm. Yeah, it's 88 or 89 degrees, I think.
Oh, wow. Okay.
There's only a small region around the poles that it cannot see.
Okay, interesting. So is there only the one satellite then?
There's currently only the one satellite, yes.
Okay, so to make measurements, you kind of just got to wait your time for it to be over the area of interest. And, well, the Earth would rotate underneath it, right, as it's in polar orbit.
Exactly.
Yeah.
Exactly. So you have one track. Actually, you have 6 tracks because there are 6 laser beams that are spaced out in a fixed pattern, and then the Earth rotates for the next orbit, so that pattern will be shifted. And the way it's set up is that if you're at high enough latitude in the Arctic or Antarctic, those adjacent sets of tracks will actually overlap.
Right.
So even though the exact revisit interval, so until the satellite is on the exact same nominal orbit, is about 90 days, you don't have to wait 90 days to get a new data point. So it happens more quickly because adjacent orbits are overlapping. And you can imagine there is that exact 90-day interval, but you have your ascending and your descending portion of the orbit. So there's one half where the satellite travels towards the North Pole, and then one where it travels toward the South Pole. So in the middle of that 90-day interval, you get an opposite repeat in a way, where your descending orbit has the same track as the ascending orbit had 45 days ago.
Okay.
Okay.
Got it. So it's almost like, the lines of longitude, you get that cosine of the latitude effect.
Yeah.
Right, with the bunching up of the orbits near the North and South Pole.
Mm-hmm. Yeah.
Right. So what do you do when you actually go to Greenland? So what's the idea of doing a field trip to a place like that? And how does this play in with everything?
Mm-hmm. Yeah. So our project has the goal of characterizing how deep the light from the satellite penetrates into the glacier ice. And I remember the first science teams meeting at NASA Goddard that I got to go to. The science team lead for the mission had a slide up, her very first slide that she had made from before the mission launched, and it had all the biggest risk factors on it to the mission. One of those was, for example, the door might not open. So the big telescope that the satellite uses to collect the light, there was a door on it to make sure that the detectors are shielded in case that the satellite comes out of the spacecraft pointing at the sun. And there was always the small chance that the door might not open, which it has. Everything's fine. And the very last point on the slide was that the penetration of green light is unknown and might be uncharacterizable. So what does that mean? Ice and snow are made out of water. And the only reason why snow appears white is that it scatters light in a somewhat chaotic manner. But you may remember that if you pour yourself a glass of water from the tap, that the water is transparent. So what happens, even when the water is arranged in these small crystals and droplets, like in a cloud or in snow, is that that light penetrates into it to some extent because it's made out of water, which is transparent. Why wouldn't it penetrate into it? So the actual signal that the satellite sees for glacier ice or snow is not the true surface, but some average reflection that's returned at some depth of the volume.
Right.
Which by itself is not a big problem. So if you're always looking at the same surface, let's say you're always looking at the same type of glacier ice that hasn't changed its properties, which that's a big if, then you're comparing apples to apples if you look at subsequent passes of the satellite. So everything's fine. But what if your land cover changes throughout the year? What if you're going from solid land to snow? If you're going from glacier ice to snow, if you're going from water to sea ice that is covered in snow throughout the seasons. So now you're having these different biases that could exist throughout the seasons and on different surfaces. So we build a field instrument that can measure the penetration depth of green light. So that was the first point that we were hoping to address. Then we can simply give the headquarters a number. This is the ballpark where the light penetration is in for the snow we found in Greenland, for the bare glacier ice we found in Greenland. We can tell them it's probably 2 centimeters off, but on average, you're mostly fine, and everyone can
breathe easy,
can chill out a little bit.
So is this device...
Not that anyone's really worried that this is a problem, but then here's the catch: because we think there is a signature of that penetration in the satellite data, we think that we can invert the whole process and measure the penetration depth from the satellite data. And now you have new information that you can get out of the satellite data because that information is linked to how porous the snow and the ice are.
I was just thinking, is the device something that the laser light would go into, or is you actually looking at the area that the light would hit and measuring, I guess in situ, how far on average that light penetrates before being scattered back up? You know what I'm saying? Are you doing it like in a laboratory environment where you have a known device of known characteristics and allowing the light to go into and then come back, scatter out of that? Or are you actually watching it scattered, from the actual natural material itself?
We can do it outside with the natural material. So what we build is kind of a small version of the instrument that's flying on the satellite. So we have our own pulsed green laser. We have our own photon counting detectors that can time the arrival time of the pulses. And so we can set up a measurement where we send in a pulse of light and we have a detector that measures when it comes back out of the ice, except that we know where the laser and the detector are relative to the surface. So we can look at what happens below the surface by putting our optics directly onto the surface of the ice or the snow. What we can also do, and that's a stronger signature, is we can put our laser and the detector in different positions and look at light that gets transmitted sideways through the snow or the ice. So now we're only looking at the component that interacts most with that medium, and that way we can get more information. So it's in the end, again, a timing measurement. So think of it that way. If there was no scattering happening in the medium, which is what it would be if you had clear water or just air, then the light would just go straight from the laser to our detector. It would go to the bottom of the glacier and come back out. So you would have kind of a free space reference length that if you go sideways from your laser to your detector. So for example, let's say your laser and your detector are 3 feet away from each other. So the light should take about 3 nanoseconds if it was air. You have to take refractive indices to account, which is 1.3 for water. So it would take roughly 3.5, 4 nanoseconds for a light to get there. Now, what you actually see is that it takes more like 100 nanoseconds because the light gets bounced around and reflected and refracted by all the grains and crystals and other things that are happening in the ice and the snow. And that is the signature that you're looking for. So the question that our instrument is asking is, how much longer does it take light to propagate through that medium than it should?
Okay.
And that is equivalent to the information for how deep does the light from the satellite penetrate into the medium.
So just out of curiosity, when the laser reaches the surface, how on average is the size of that illumination, that spot or that area? Can you give us sort of a rough idea of what we're looking at?
They think that the diameter is about 20 meters.
20 meters.
Oh, wow.
And so that light gets scattered back up to the satellite? They can measure that scattering?
Some of it, yeah.
So how faint would that be?
Right. That's what I'm thinking. Wow.
How faint would that be? So let's assume for simplicity that the surface scatters all the light back. There's no absorption and there's no absorption in the atmosphere.
Right.
Mm-hmm.
So your ground, whatever it is you're hitting, just scatters light anywhere, right? That's the behavior of light that we observe in the real world. If the surfaces of the desk that I'm sitting in front of is not reflective like a mirror, but you get these diffuse reflections. So the light kind of propagates out in like a spherical pattern and goes everywhere. So if you now go up to the altitude where the satellite is, you can imagine that light is distributed on this hemisphere around the point that it got scattered from.
Mm-hmm.
So you can now calculate, because you know the elevation of the satellite, what the area of that surface is.
Yeah.
And then you take the area that's covered by the telescope, by the collection optics on the satellite, and divide that by the area of the whole hemisphere, and that's a fraction of the light you actually collect.
Right.
And that fraction is something like 10 to the minus 18.
Right.
Wow.
Yeah. Yeah.
Yeah,
That
that's
said,
amazing.
we have detectors that detect light on that order for telescopes. So
Yeah.
Well, that's half of it. You also start out with a lot of photons.
yeah.
Right. Yeah.
So you between the two, yeah.
And the distance is relatively short.
Relatively, right.
Yeah. So
Relatively,
that helps too.
it's in low Earth orbit, so about 300 miles or 500 kilometers.
Yeah. Not bad. Anyways, I guess it's time to wrap this up. So thank you very much, Marcus.
Yes.
You know, we never got to that special word,
Which one?
entanglement.
Yeah, we didn't.
Didn't really go in there. But
We'll have to try again with somebody.
we'll have to get Marcus back on again and maybe dive into what entanglement is all about and how that plays.
Absolutely, we can defer that to part 2.
Yeah, it sounds good. Now, one of the things, if you're interested in maybe working with Marcus
Right.
on his research, one of the things you could do, of course, is come here to the University of North Dakota. We do have online programs. We also have programs on campus, such as the ones that you could be involved with potentially with Marcus and his research. So if you find any of this stuff exciting, there are places for you to go to learn more about this.
Absolutely. And so come join us.
Now, our next podcast.
Absolutely.
Yep. So there, Marcus is
Always looking
willing.
for undergraduate and graduate students. We have plenty of work to do in lasers to align.
There you
There
go.
we go.
We need warm bodies. That somebody
need more
once
people.
told me. Now the other thing is our next podcast will be next Tuesday.
Mm-hmm.
So that would be December already, December the 3rd.
Yeah.
So the year is winding down pretty rapidly here. Now we always leave you with a quote at the end. I had made an assumption, and you know what assumption means when you do that, so I won't say it out loud. You can think about it. Send me an email if you want to know what I'm talking about. But I made an assumption we would hit entanglement. So the quote is about entanglement.
Okay.
So you can kind of save it for the next time that we do talk about it. It's actually by the person that coined the term entanglement.
Oh,
So
okay.
quantum entanglement. Erwin Schrödinger back in 1935 wrote a paper describing entanglement. And here's what he said. So just a sort of an excerpt from his paper. I would not call, and it's entanglement, one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought.
That's cool. I like that. And he's probably right.
Yeah, exactly. So with that, thank you very much, Marcus, for joining
Thank
us
you.
today. If you like this podcast, don't forget to give us a thumbs up. We always appreciate that. And we'll see you next time.
See you next time, folks. Have a good evening and happy Thanksgiving.